Today I'm going to give an introduction to wireless network standards, then I'm going to move on to antenna technology, and we will conclude with wireless access points. There is a whole plethora of information to impart, not a lot of time, so let's go ahead and begin this session. I'm going to begin by giving an introduction to wireless network standards. To talk about the standards, I need to introduce you to the IEEE 802.11 specifications. These are a set of specifications that deal with the data link layer and the physical layer of the OSI reference model. These establish how wireless network communication can occur. The 802.11 standard specifies the use of unlicensed radio frequency bands as the carrier for network traffic. It also specifies that network communication will be half duplex in nature, and that it will be implemented using carrier-sense multiple access with collision avoidance, or CSMA-CA. Carrier-sense multiple access with collision avoidance technology requires that devices only transmit data when no other data transmission signal is present on the carrier wave. Now, the 802.11 standards have been amended over time to become our common standards that we see today. These standards include the 802.11b wireless standard. It was commercially released in 1997 and operates within the 2.4 GHz Industrial, Scientific, and Medical, or ISM, radio frequency band. Now, within the 2.4 GHz RF band, it uses multiple channels that are 22 MHz wide. There are 11 separate channels, of which only 3 do not overlap. 802.11b has a theoretical throughput of 11 megabits per second, and it is compatible with the 802.11g and N standards. Then there's 802.11a. It was also commercially released in 1997 and operates within the 5 GHz unlicensed National Information Infrastructure, or U-NII, radio frequency band. It offers up to 23 separate channels that offer a bandwidth of 20 MHz each. None of the channels overlap. 802.11a has a theoretical throughput of 54 megabits per second. It is not compatible with any other standard. 802.11g was commercially released in 2003 and operates within the 2.4 GHz radio frequency band, just like 802.11b. It also offers a bandwidth of 20 MHz on 11 separate channels. It has a theoretical throughput of 54 megabits per second, and it's also compatible with 802.11b. It's also compatible with 802.11n and 802.11ac. And that brings us to 802.11n. It was commercially released in 2009 and can operate on both the 2.4 GHz and 5 GHz radio frequency bands at the same time. It uses a 20 MHz wide channel within the 2.4 GHz band and a 40 MHz wide channel within the 5 GHz band. It has a theoretical throughput of 600 megabits per second through the introduction of multiple input and multiple output MIMO technology and beamforming. And it is compatible with .11b, .11g, and .11ac. And that brings us to 802.11ac. It was commercially released in 2013 and operates on the 5 GHz radio frequency band. The available bandwidth varies by administrative settings and can be dynamically changed by the wireless access point based on how much radio frequency interference, or RFI, is present and how many users are on the wireless network. 802.11ac has a theoretical throughput of over 1 gigabit per second through the introduction of multi-user, multiple input and multiple output technology, or MU-MIMO, technology, and beamforming. 802.11ac is only compatible with 802.11g and n. So why broadcast a wide signal to a specific device when it's possible to target that device specifically? This is the question that beamforming answered. Once a device makes a connection to an access point that is capable of beamforming, the AP will auto-tune its antenna and transmitter to more specifically target the device when communication occurs. This can reduce RFI and increase throughput on the wireless local area network. While 802.11n allowed for beamforming, it was not a standardized option until the implementation of 802.11ac. Since we've covered the standards, let's move on to antenna technology. First up, the basics. Antennas are used to broadcast and receive radio frequency signals, and they fall into two basic categories. There are omnidirectional antennas, which are designed to broadcast and receive signals in all directions. Then there are unidirectional antennas, which are designed to broadcast and receive signals in a specific direction. Antenna placement and type of antenna will have an impact on wireless local area network performance. Both MIMO and MU-MIMO are technologies that allow for more than one spatial stream to be transmitted and received by a single device through the use of multiple antennas. MIMO allows for up to 4 spatial channels, while MU-MIMO allows for up to 8 spatial channels. MU-MIMO also allows for a single signal to be spread across multiple transmitters. This accounts for the multiple user part of the name. Let's conclude with a discussion on wireless access points. The wireless access point is a foundational piece of the wireless local area network. The wireless access point, or WAP, can also be known as an access point, or AP, and it creates a point of entry for wireless to enter the more traditional wired networking environment. The AP can also be used to join other types of networks. Wireless access points in most cases use unlicensed radio frequency bands in order to communicate with devices. One or more antennas are used in order to radiate and receive radio frequency signals in a half-duplex manner. Wireless routers are common in the small office, home office environment.